Lisa. So today I'm going to start our presentations on the electronic system subject for the project. But first, I will explain to you briefly what is electronic system. Electronic system are systems which are designed to process electrical signals. Non-electrical input signals are converted into an electrical form by using sensing units. Switch unit could be used to convert the signal into an electrical form when its pressure applied on a mat. Now we move to the questions. Based on these projects, we need to design and stimulate the electronic system as shown in figure 1, which is we need to construct a circuit consisting of oscillator 1, oscillator 2, active low pass filter, rectifier, voltage regulator, loads, and summing.
Hi, my name is FARHANAJWA binti Muhammad FAUDZI and my number matric is B08221010C. And now I'm going to present oscillator 1. The calculation have two different type feedback loops. First, positive feedback loop and second one is negative feedback loop. The positive feedback loop given resonant frequency for 1 kHz and assume for value capacitor as 1 nanofarad. Therefore, C1, C2 and C1 nanofarad. Then, we find the value of R by using the formula and the given frequency FR equal 1 kHz equal 1 per 2 pi RC. And we change R to FR. R equal 1 per 2 pi FRC. And calculate 1 per 2 pi multiply 1 kHz multiply 1 nanofarad. And the answer 159.15 kilo ohm. The nearest standard value 159 kilo ohm. So R, R1 and R2 is 159 kilo ohm. We calculate the frequency with the calculate value of R and C to check whether it match the specification. FR equal 1 kHz equal 1 per 2 pi RC and 1 per 2 pi multiply 159 kilo multiply 1 nanofarad and the answer 1 kilo ohm. Next, negative feedback loop. Use gain formula to calculate RS and RF. AV equal 1 plus RF per RS and the given 3. Keep in mind the oscillator gain must be close to 3, meaning the oscillator must be sustained. The oscillation will stop if the gain is less than 3. If the oscillation is more than 3, distortion will result for the oscillation. So, 3 equal 1 plus RF per RS. 2 per RF per RS. And we change to RS multiply equal RF and let RS equal 33 kilo ohm. And we get the answer 99 kilo ohm and the nearest standard value is 98 kilo ohm. Next, we move to simulation. And we transfer all the calculation to the multisim in RF, RS, R and C. For RF, value is 68 kilo ohm, RS 33 kilo ohm, R1 and R2 159 kilo ohm, and C1 and C2 1 nanofarad. And we run the simulation. And yeah, the final result for V peak to peak 1.18 volt, frequency 993 Hz. And we got the good wave.
My name is UMAIRA binti HASHIM. My matric number is B0822101153. I will explain about the oscillator 2. This is a wind bridge oscillator whereby there are two RC that connected together in the circuit. The DC supply R connected to the VCC is 15 volt and the resonant frequency is 20 kHz. In this circuit, I am using the capacitor with value 2 nanofarad. Next, we calculate the resistor value, which is 3.4 k ohm, by using the wind bridge oscillator frequency formula. The frequency resonance that we get by using the 2 nanofarad capacitor and 3.4 k ohm resistor is 23.41 kHz. Lastly, we calculate the gain for RF and RS resistor, where RS is 48 k ohm and RF is 2 times of RS, so the RF is 60 k ohm, but we use 90 k ohm resistor in our simulation.
Okay, now I will explain about the circuit simulation. This is the oscillation of the wind bridge oscillator. As we can see that the oscilloscope is channel 1 is connected to the output of the IC, and the other oscilloscope is connected to the ground. So when we run the circuit, we will get the output, which is this is the output. As we can see that the frequency of the frequency is 19.2 kilohertz, which is near with the value of the question, which is frequency resonance, which is 20 kilohertz. That's all for me. Thank you.
My name is FARAH binti JAFFNY. My matric number is B0822101185. I will taking over summing amplifier circuit. Summing amplifier circuit is basically to combine the voltage of manipulating input into one output voltage. So in this case, we have two input voltage from the oscillator. We are moving on into calculation. So the formula for define Vout is RF V1 over R1 plus V2 over R2. So that we have given RF is 1 kilo ohm. V1 is V peak to peak for channel 1. V2 is V peak to peak for channel 2. Then we can eliminate the 1 kilo ohm of resistor. So the answer of Vout is 1.322 volt. Here is oscillator 1, wind bridge. Oscillator 2, wind bridge. The output of summing is channel 1, V peak to peak, channel 2, V peak to peak. So divide it, as you can see in calculation, is it will get 1.322 volt, which is near to the exact value from the calculation. That's all. We will continue to my other friend.
Next, we will move to active filter LPF. What is active filter LPF? Active filter, such as an active low-pass filter or filter circuit, they use an operational amplifier op-amp as their main amplifying device along with some resistor and capacitor to provide a filter-like performance at low frequencies. The application of active low-pass filter are in audio amplifiers, equalizer, or speaker system to direct the lower frequency bass signal to the larger bass signal or to reduce any high frequency noise or hiss type distortion. Next, for the calculation for the active low-pass filter, we are going to use the second order Butterworth response, as you can refer to the table that I prepared. For the damping factor, DF equals 2, and while R3 over R4 equals to 1.414, hence R3 over R4 equals to 1 kilo ohms. Next, R3 equals to 0.586 times R4. We need to substitute the value of R4 with one case, and then we will get 586 ohm. While given FC equals to 8 kilohertz, for the FC we need to use the formula of 1 over 2 pi RC. So we need to assume C as 10 nanofarad. So we need to substitute the value of FC and C. So we get 2 pi times 8k times 10 nano, and then we will get 2k ohm as the final results.
Hi, so now we will continue to the simulations that I use in multisim, and here I already construct the circuits based on the active filter, and here I'm using function generator, op-amp, and also a Bob Porter. Bob Porter is used to produce a graph based on our circuits. I'm also using a capacitor of 10 nanofarads here, and the resistor with the value of 2 kilo ohms. And I'm also using the VCC is 15 volts and VDB with negative 15 volts. So now I will run the simulations. And then we'll get this graph. The first half of the graph is constant until we hit 1.054 kilohertz, and then the graph will decrease. That's all from me. Thank you.
I'm going to explain about my part, which is rectifier. Rectifier is an electrical device that converts alternating current AC, which periodically reverse direction, to direct current DC, which flows in only one direction. The reverse operation, which is DC to AC, is performed by an inverter. The question given is we need to design and simulate a full bridge rectifier circuit. The first part is we should do the calculation. VDC equal to 2 V peak divided by pi. V peak is 20, so the total is 12.732 volt. Next, V out is equal to V peak of input minus to 1.414, so the total is 18.6 volt. Lastly is the voltage of the ripple is equal to 1 over 2 multiplied by the frequency, which is 30 Hz, and multiply with the capacitor 1 microfarad. The total of V ripple is 204.167 millivolt. After the simulation, we need to calculate the measured value. V peak of input is equal to 19.9 volt, and the output voltage of ripple is 3.89 volt.
Okay, next, this is the full wave bridge rectifier circuit. As we can see, the input is connected to the channel 1 of oscilloscope, and then the channel 2 of the oscilloscope is connected to the output. So we are going to simulate this design to get the result. Okay, this is the result of the full wave bridge rectifier. As we can see, the frequency is 30 Hz. The period is 33.3 millisecond, and the peak to peak is 39.9 volt, and then the maximum of the waveform is 19.9 volt. And that's all for the rectifier circuit. Thank you.
I will continue with my part is voltage regulator and load. In this my part, for the voltage regulator part, the calculation is the output for voltage is 5 volt and the voltage regulator type in the circuit is op-amp shunt regulator circuit. So the load is rated equal to power is 1 watt. So to get the R4, I use the formula of power, which is a P equal to V square over to R, and then I will change the formula because I want to get the R, so the formula change to R equal to V square over P. Then I will continue with the calculation is R equal to 5 square because 5 it's mean for voltage, and over to 1 because 1 is for power, and then I will get the answer equal to R 25 volt. Next, I will calculate about the output voltage from R4, same with output voltage with R2 parallel with R3 by using the voltage divider formula. The voltage divider formula is R2 over R3 multiply with VR. In this calculation, R2 is a 2 ohm, and then R3 is also 2 ohm, and the calculation will be 2 ohm over 2 ohm multiply with 5 because 5 is VR, and then the answer will be 5 volt. Next, the Zener diode compare with the feedback voltage from R2 parallel with R3. So there will be the difference in this calculation with the measured value. So the first, to find the Zener diode is a voltage, diode voltage, is the formula is a VO equal open bracket 1 plus R2 over R3 and close the bracket, and then VZ. VZ is represent for Zener diode voltage. So VO equal to multiply with 1 plus 2 over 2 because 2 over 2 will be R and R2 and R3. The value is same, and then the close the bracket and the VZ. So in this calculation, VO is represent for 5 volt, and then multiply with 2 because the calculation is 1 plus 2 over 2 is 2, and then VZ. So we will find the VZ is equal 5 over 2 because we want to find the answer of VZ, and then equal VZ. The answer is 2.5 volt. Lastly, in the table of the calculated value and measure value will be similar or slightly different for the value. So the parameter is a voltage across Zener diode. Calculated value I get 2.5 volt, and the measure value is 4.805 volt. And then the output voltage is 5 volt, and then measure value is 4.98 volt. The load voltage is 5 volt. The measure value is I get a 4.98 volt. So the lastly power at load resistor calculated value is 1 watt, and then the measure value I get 992.189 milliwatt. For this, for the circuit, this is the circuit that constructed for voltage regulator and load. So this is the load part, okay, for the voltage circuit. Then the voltage regulator, we use the DC interactive voltage to get to adjust and get 2.5 volt. Okay, so the circuit will be run. So this is the value they show for this circuit. So firstly, the value show for the Zener diode, and the voltage got 4.805 volt. Then I will continue for the multimeter at the R2 and R3. This is R2 and R3 is parallel, so the value will be similar. Okay, first one I got for R2 I got 4.98 volt, and then the R3 I got 4.98 volt also, the similar lah. And then the multimeter, so lastly we use the wattmeter that to got the power, and the power will be got the value is which is 992.189 milliwatt. So this is the measure value that I got.
My name is Nur Shafiza binti Ramli. My metric number is B0822104448. I will present for my part is load. The load play important roles in electronic system block diagram, such as determine the power consumption, voltage and current rating, and input and output interface. This is the calculation for the load. Given power load requires is 1 watt. The voltage load is equal 4.917 volt. Power load equal voltage load square divide resistor load. Resistor load equal voltage load square divide power load. The value of voltage load is 4.917 volt. So 4.917 volt square divide 1 watt. So the value of resistor load is 24.18 ohm.
The value for DC supply that used is 4.917 volt based on the calculation. The DC supply was connected parallel with the resistor. The value for resistor that used is 24.80 ohm based on the calculation. The simulation circuit was connected to the ground. When the simulation are run, the lamp will on.